Okay, so now I'm going to show you how to make a normal distribution in R. So the first thing we do in R is we set the size of the graph window. So dev new with 5 height 5, it's just saying give me a graph window with the dimensions of 5 by 5. I think it's 5 inches by 5 inches, so 5 inches wide by 5 inches tall. That's the quartz 2. You see it's just a blank window for graphs that we'll use later. So now in your assignment, I give you a mean and a standard deviation for cost because we're modeling cost as a distribution. So our norm, that's a random normal variable. So random normal variable. We're going to say one observation with a mean of 45,000 and a standard deviation of 100,000. So it gives us one observation there. Remember, the distributions are also random number generators. So when I ask for one observation, one draw from a normal distribution. So take one number from a bell curve that has, and the bell curve is defined by a mean of $45,000 and a standard deviation of $100,000. Those means and standard deviations are the same that I give you in the assignment letter for your cost distribution. So if I do it 3 times, I'm going to get 3 different numbers, right? It's a random number generator. And if you do it enough times, you will have a mean about 45,000 and you will have a standard deviation of about $100,000. If you just take one number from it, you'll get a different number each time because it's a random number generator, so a random normal variable. So the first time I did it, I got $36,685.59. The next time I did it, I actually got a negative cost, negative $13,000 and negative $13,656.51. The third time I did it, I got another positive one, 164,489.10. So each time I ask for a random number from that distribution defined by the mean and standard deviation, every time I do that, I get a different cost. And then I do the exact same random normal variable, but instead of one draw, I ask for 1,000 draws. Now, when I ask for 1,000 draws, you could list out all 1,000 numbers, and I will do that later. The easier way to do it when you have 1,000 data points, 1,000 draws from that normal distribution, the easier way to see that than listing all 1,000 of them out is to summarize it. So look at the minimum, the maximum, the mean, and the standard deviation. First quartile, that's the 25th percentile. Median, that's the 50th percentile, the middle number. Third quartile, that's the 75th percentile. The first quartile to the third quartile, that's called the interquartile range, that 25th percentile through the 75th percentile. So the means are different each time I do it. So the first time I took 1,000 numbers, the mean was $44,600. Next time I did it, the mean was $42,418. And the third time I did it, the mean was $45,860. So we asked for 1,000 draws from a normal distribution with a mean of 45,000. If we pull 1,000 numbers from that, because they're randomly drawn, the mean's not going to equal 45,000. But we pulled 1,000 numbers from it, so the mean is pretty close, right? It's not 45,000, but it's 44,000, 42,000, 46,000. The standard deviation's same thing. So standard deviation, we said draw it from a normal distribution where the standard deviation is $100,000, like in your assignment. The first time we did it, we got a standard deviation of $99,428. Next time, $94,924. The third time we did it, standard deviation of $100,732. So when we take 1,000 draws from a normal distribution, we set the mean 45,000. We got a mean pretty close to that if we take 1,000 numbers from that. 1,000 random numbers from that underlying distribution. Standard deviation 100,000 in the underlying distribution. We pull 1,000 numbers, we get a standard deviation pretty close to $100,000. It's not exactly 100,000, but it's $99,500 or $94,924 and so on. So the means and the standard deviations are close to what we give it for the distribution. But when we take 1,000 random numbers from it, the means and standard deviations are pretty close to it. And you can see 1,000 numbers here. So the first row, all the way down, so 1,000 cost data points. So draw 1,000 cost estimates from that distribution defined by the moments. The moments for a normal distribution are just the mean, moment 1, and standard deviation, moment 2. So normal distribution is just defined by these two moments. So all you have to give it is the number of draws you want, the mean, and the standard deviation. An easier way to see the 1,000 data points rather than just looking at them is to make a histogram of it. So ylim there, it's just setting the y-axis, goes from 0 to 0.000005. That's just so I got a y-axis that fits the probability distribution. Prob equals 2, that's just setting it as a probability that I'm interested in the probability density for the distribution. These distributions are also called PDFs, so the underlying math that spits out these random numbers is called a PDF, for not for portable document format, for probability density function. So the probability density function of a normal distribution. And you can see the histogram there is, it looks like it's a bell curve, right? We took 1,000 numbers from it. 1,000's enough data that it's going to approach a bell curve. It's not exactly a bell curve, but the more random numbers you pull from that distribution, from that random number generating distribution, it's going to approach something that looks like a bell curve. So now let's add the bell curve on top of it. So dnorm, normal distribution, fit the curve, dnorm, normal distribution. So I'm going to add the bell curve to the histogram so we could see how the histogram is approaching a bell curve. So it's a histogram, it's showing the density, the probability density function of those different numbers we put. So most of them are right around the middle where it's, remember we said that mean is $45,000, and then fewer of them are at those endpoints because the normal distribution is a bell curve. Remember, it's got these tails on the right and on the left side with a few data points, and then most of the data points are right in the middle. So let's fit the curve using the empirical mean and the empirical cost. The empirical mean and the empirical standard deviation of cost. So remember we said that the theoretical distribution, the population distribution, has a mean of $45,000 and a standard deviation of $100,000. Our actual mean and our standard deviation are a little off of those numbers because I showed you earlier. Because it's a random number generator, you don't get exactly the mean and the cost that we set the distribution equal to, but it approaches that. So add equals true, it's just saying add, instead of making a new graph with the bell curve, add the bell curve to the histogram. So add it to the bell curve, yes. Color equals dark red, so make the bell curve dark red. You can change to dark blue, green, orange. Try different names of colors in there and see which ones it could do. And now let's do the same thing using the theoretical mean, 45,000, which we set it equal to, and the theoretical standard deviation, 100,000, that we set it equal to. Add equals true. Add that theoretical distribution to the empirical distribution, right? So put two bell curves on the same graph, one using the mean and the standard deviation from the distribution, and one using the mean and the standard deviation from those 1,000 draws that we pulled from the distribution. Let's make this one dark blue. It's going to be almost exactly the same. So what if it happens if you mix red and blue together? You get purple. If you mix dark red and dark blue together, you get dark purple. So you can see there that the curve turned purple. Its red and blue ones are almost identical. You can't really even see the gap between those two bell curves because the mean's about the same and the standard deviation's about the same. And you can see that drawing 1,000 data points is enough data that when you take 1,000 random numbers from it, it's going to look like a bell curve. And you'll get a different answer each time you do it. So each time you run that, you're going to get 1,000 different ones. In triage, you're going to say we do the entire cost effectiveness analysis 1,000 times, simulate the entire cost effectiveness model, run the entire tree, the entire analysis 1,000 times. And since we have 1,000 cost data points, you're going to get 1,000 ICERs, you're going to get 1,000 net monetary benefits, and that will let you unlock different graphs. So unlock the acceptability curve, where it graphs the willingness to pay against the probability that's cost effective. And then it's going to do a confidence ellipse like we'll do in the last example for class the last case, where it's going to actually draw a 95% confidence ellipse oval around the data points. So you draw 1,000 random cost numbers is going to give you 1,000 random ICERs. And you can distribute everything in the model, but as long as one thing's distributed, in this case cost is the only thing we set a distribution for, then it's going to give you 1,000 ICERs and give you a range of ICERs. The ICER is going to have a mean and a standard deviation and so on, and unlock some new graphs.